quadratic would be a polynomial function. A cubic would be a polynomial function. Basically, I need that my exponents here, any exponents here, I want to be positive whole number exponents. So variable exponents should be positive whole numbers. We're not going to put any variables in the denominator. We're not going to take a square root because a square root would technically be a 1/2 power. That's not a whole number. I'm not going to take the absolute value. I'm not going to do, so basically just our normal, I shouldn't say normal, but I could have cubics, I could have quadratics, I could have 4th degree, 5th degree, but we're just going to have terms like that. So in your homework, they're going to ask you to identify which of the following are polynomial functions. So we're just going to look through this and say either yes, it's a polynomial function, or no, it's not a polynomial function. Okay? So I've got 4 different types here that we're going to try and do this for. And as you're writing it down, I'm going to take attendance really quickly. Okay. So identify which are polynomial functions. When I look at that first one, I've got 4x to the third plus 2x plus 1/2. Here's what I'm looking for. Here's my variable. That's a positive whole number. That's a positive whole number. This one doesn't have a variable, but that's okay. If it did, it technically would be x to the 0. That's not a negative exponent, so that's okay. So this one I would say is a polynomial function. Technically, that one, we identify it by its biggest exponent. We could call that a cubic function. This next one over here, basically, as soon as I do something a little bit strange to it, we're going to say not a polynomial function. Now, don't try to simplify this and say that's the square root of this and the square root of this, and I can take the square root of 25 and I can take the square root of x squared. You can't take square roots of, or you can't separate square roots of individual quantities. And technically, a square root, like I just mentioned a little bit ago, means it is to the 1/2 power. So that's not a positive exponent. It is positive. It's not a whole number exponent. So I'm going to say not a polynomial. Roots we call radical functions, so that is technically a radical function. This one over here, hopefully since I've been telling you that it has to be positive, that's not positive. Hopefully you say not a polynomial function. Just know they're going to try to trick you. That one I didn't try to trick you, but the way that they're going to try and trick us with ones like that, remember if we had a negative exponent, you could move it to the denominator. So they might have written this exact same problem like this. And now it is a exponent that is a positive number. It just can't be in the denominator. So if it happens to be in the denominator, we're still going to say, nope, not a polynomial function, because if I were to write it not in the denominator, it would be that negative exponent. Okay. This last one, technically a 1 and a 4. So I would say, yep, those are both positive integer exponents. So I'd say this is a polynomial function. Poly just typically means more than one, many, and nomial just means terms. So we're just adding or subtracting many terms together. Okay. Then they're going to give us a question like this. It says, write an equation for the linear function f such that f of -1 equals 2 and f of 3 equals -2. They write it in this way. And when they write it this way, they act like it's a brand new question that we've never seen before. I would argue that this is a question, granted it's written a little differently, but this is a question that probably you learned how to do back in intermediate algebra. They're just posing it in a different way, which now makes it seem a lot more difficult. They want a linear function. That's just a linear equation. Normally we write those as y equals mx plus b. Okay. and they gave us f of negative 1 equals 2 and f of 3 equals negative 2, normally I write it as f of x. So when they give us this f of negative 1 equals 2, they're actually giving you an ordered pair. And in that ordered pair, your x value is negative 1. And they're saying when I put negative 1 into whatever this function is, the y value I get back is 2. And then the second ordered pair is the x value is 3. The y value I get back is negative 2. If I gave you 2 points, you should be able to write a linear equation, and that's what we're going to do. To write a linear equation, I need a slope and a point. I've got points, I just don't have a slope. So I'm going to start this problem by finding my slope between those 2 points. So my slope, remember, you probably don't need to write this down. I'm going to write it down just kind of as overkill just to make sure we remember all this. Slope formula is just y2 minus y1 over x2 minus x1. So my y2 I'm going to say is negative 2 minus my y1, which is also 2, over my x2, which is 3, minus my x1, which is negative 1. That's going to give me negative 4 over 4, which tells me that the slope between those 2 points would be negative 1. Okay. Then I just need to write, they said write a function f. So I want it to be f of x equals, which tells me I probably want it to be y equals mx plus b form. You are going to use this as your slope. You can use either one of those as your point, and we just want to try and get into y equals mx plus b form. I personally prefer, even though I just said get in y equals mx plus b form, I prefer to write it in point slope form, meaning y minus, I'm going to use this first order here, my y value equals my slope times x minus my x value. I just am not done here. I have to solve for that. So I'm going to write that as a negative x minus 1. All I've done so far is I minus that negative, and then I distribute it all to negative 1. And then finally, I'm going to add 2 to both sides. Technically, they said write a function f, so here's my function f. Do you have to write it in point slope form first? No. You could write it in slope intercept form, solve for your b, substitute it back in, get your equation. Okay? But regardless, we should get the same answer. So those ones, I believe the first ones in your homework today are kind of like that. And just a heads up, I'm almost 99% positive if I'm remembering correctly. I think one of the first questions on your chapter 2 tests are like that. So make sure you understand how to do a problem like that. That should be hopefully easy points on a future test or quiz. Okay, rate of change is really just our slope. So remember, rate of change is just our slope, which I already wrote that down up there, but that's y2 minus y1 over x2 minus x1. You might have some problems today where they simply just say find the rate of change. They're just saying find your slope. Okay? Because all that this is doing is telling me how much my y values are changing over how much my x values are changing. Okay, then sometimes our problems are going to be more complicated than just a linear equation. And when they get a little bit more complicated, they're going to say, what is the initial value of this cubic function? Or what is the initial value of this 5th degree polynomial, etc. The initial value is really just the same thing as the constant term. So the initial value is your y value when x equals 0. But if we think back, and I know you're writing that down, I will come right back to this. If I think back to when I defined a polynomial, if my x value is 0, that'd be a times 0 plus b times 0 plus all these other terms times 0 until I get to this very last term right here that did not have an x next to it, so I could not multiply it by 0. So at time 0, all these other terms are going to go away. All that will be left is that last term that doesn't have an x next to it. So when they ask for your initial value, you can absolutely substitute 0 in, or you can just look at your entire polynomial and look for your constant term. So it's just your constant term. I was going to say at the end, but technically they don't always give it to us in standard form, so I don't want you to just automatically look at the end. But your initial value is your set number at the very end, typically. Okay, then we are going to switch to just a little bit real quick. We've talked about our correlation coefficients, our R value. They're going to hit on that a little bit more. Your linear correlation is going to either have a positive correlation or a negative correlation. When we are talking about these correlations, remember they go somewhere between 1 to -1. If it is a perfect 1, that means that those lines fall in a perfect line and it is going up as a positive slope. If it's a perfect -1, that means those points fall in a perfect line and it's just a line that's decreasing. They're going to ask us in just a second here to describe the correlation. A 1, a -1, those are strong correlations. Okay, so besides positive and a negative, the other words we can use is we could use a strong correlation. Strong would mean it's close to either a 1 or a -1. We could say it has like a moderate correlation. Moderate, I would argue, is anywhere from maybe even like 0.5 to like 0.8. So kind of in that middle one. It's still, I can tell that it's going up, but the points are a little bit more spread apart. And then we are going to either call it a weak or we'd say no correlation. A weak or no correlation would kind of be, if I were to draw a line, I don't know if I would draw the same line twice in a row. Like, I don't know if I would draw the line this way, or would I draw the line up here or down this way, or it's just, it doesn't look like they're forming one. Okay. So example 3 here, don't take too much time as you're sketching those, but example 3 here, we're going to try to kind of get some descriptors. In your homework today, they truly will already have graphs sketched out for us, and they'll say describe the correlation. I want 2 things when you're describing the correlations. I want to know, are they positive or strong? Sorry, positive or negative? Not positive or strong. Positive or negative? And then I want to know, are they strong? Are they moderate? Are they weak? Or is there none? Now, if there's no correlation, you can't tell me that it's positive and you can't tell me that it's negative. So it would just be no correlation. Okay. So for that very first one, which I try to make look like the 5 on the dice or on a number cube, whatever you want to call it. For that first one, I don't know where the best line would go. I could draw a line like this, and it would go through them through 3 of the 5 points, and I would say, well, that's a positive. But at the same time, I could draw a line like this, and it would also go through 3 of the points, and that would be a negative. Or I could be like, well, what if it's like this, and it's only going through 1, but then it's close? So see how I can't really tell where that one needs to go? So this one I would say has no correlation. And when we're saying no correlation, we're saying there's no linear correlation. There's no line that's going to be really good for those points. For these next ones, sometimes what I also do is I kind of draw like an oval around the points. So for this one, I'm not drawing a line, but that's a somewhat narrow oval. And as I look at those points from left to right, it's going up, 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 up. So I would say that this one is positive. And since it's a somewhat narrow one, I would say it's a positive, strong correlation. Versus this next one, if I were to try and draw an oval around it, I can still see that those points are going down when I look at it left to right. So I can say that this is a negative, because they are, in general, decreasing. But my oval is a lot wider, so I would say negative. You could say that it has a moderate correlation. If you said, well, I said weak, I'd say I can't really argue with you because it's definitely not strong. So if you said negative and moderate, negative and weak, I'd be like, yeah, that makes sense. Okay. So strong doesn't necessarily have to mean it's a perfect one. It just has to mean it's pretty close to that one. Okay. Then we are going to write, so that's everything so far has been for linear equations. Now we're going to shift gear because I said that this, I believe I said linear and quadratic modeling. So now we're going to talk about quadratic equations. Okay, so vertex form is for a quadratic equation. Normally, you have been told to write quadratic equations like this. Ax squared plus bx plus c. We are going to try to take quadratic equations written like that and rewrite them into a new form. We're going to try to get them in what's called vertex form. Vertex form looks like this. Because if I can get them written like that, then I can use my knowledge of transformations and I can actually draw a really accurate graph of that quadratic without having to make a table, without having to sketch a graph, without having to do basically any, well, no, I can make a graph, I can sketch the graph. This one right here, when I had a quadratic, I would have had to create a table, plot the points, and try to draw it. This one, if I multiply by a number on the outside, the A out front will tell me if there's a vertical stretch or a vertical shrink. The A out front will also tell me, is it opening up or is it opening down? That A out front is the exact same A that was out front here. So those are truly the same things. Okay. If I add on the inside, or technically subtract on the inside, anything inside tells me if it moved left or right. So that's going to tell me how far left or right it goes. So H tells me the left or right. And then finally, the adding on the outside, that plus K on the outside, is going to tell me, did this graph move up or did this graph move down? So the K is going to tell me if it moved up or down. Just a really quick reminder, parabolas normally look like this. If they're opening up, if they're opening down, it's just flipped. The point right here in the exact middle, we call that our vertex. And that point in the exact middle is going to have an ordered pair, HK. Lining up with this, how far left, how far right. So when I say that it moved left or right, I'm going to take that center point and I'm going to move it left or right. And if I say it moved up or down, I'm going to take that center point and move it up or down. And then I'm going to try and graph it from there. Okay. Okay, so we've got a few steps for writing this in vertex form. I'm going to give you guys a second to get that there. There are two ways that you can write this in vertex form. One way, and the way that I used to do it, and it's great mathematically, and it truly is still works, but I'm not going to make us do it this way because it's a lot of extra work, is you could use our completing the square process. So if you remember back in chapter P, we had to do completing the square in order to solve, and everybody hated that method because it's a lot of work. I get that. It works, and it gets you perfect vertex form. Another way is to remember a skill back from algebra, which is what we're going to do. I told you this point right here is the vertex. Back in algebra, you also learn about this thing called your axis of symmetry, and your axis of symmetry goes right through the middle of that graph. I'm going to label that my AOS for axis of symmetry. And you had a formula back in algebra 1 that said if you want to find that axis of symmetry, it's the opposite of B over 2A. If you can have that memorized or written down in your notes, we can get our answers in vertex form a lot easier and a lot faster than having to do completing the square. Okay? Because this x value right here, if that's the axis of symmetry, it's going through the middle, which means that whatever that x value is right here, that in turn is what goes right there for my vertex form. So what we're going to do first, or steps for writing this, the first thing we're going to do is we're actually going to make sure it's written in standard form, ax squared plus bx plus c. So sometimes they'll give us problems where you'll have to FOIL something out or combine like terms and move things from one side to the other side, but you want to get it in standard form first. Because if it's in standard form, oops, I didn't give myself a lot of room, then I can find my axis of symmetry. And I can find my middle of my x value, middle of my parabola. Once I found that parabola, then what I can do is then I can substitute that in. To find my y value. When I find my y value, what I'm actually finding is the y value right there. And once I have that, we should be able to just quickly substitute things in and have it in vertex form. Okay, so if you can remember this formula right here, that's going to be the trickiest part. Okay, so we're going to try, and we're going to get interrupted for lunch here in just a little bit, but we're going to at least start it. We're going to try to write this equation in vertex form. I also, once it's in vertex form, want you to be able to identify the vertex, the axis of symmetry, and any transformations that happened. Okay. This one, this f of x equals x squared plus 8x minus 10 is already in standard form. So I don't have to combine like terms. I don't have to move anything from one side to the other side. So a lot of times step 1 is already done for us. What I want you to try, and we're probably going to get interrupted here pretty quick, see if you can find your axis of symmetry. Even though they said right in vertex form first, and then we'll find the axis of symmetry, we're going to do it in kind of a backwards order. We're going to find our axis of symmetry first. So that being said, what is my b value here? 8. So I want negative 8 over 2 times 1, and we will finish this when we come back from lunch. So friends at home, I'm going to pause or stop this video